React but Maintain Your Equilibrium Part 1 is an episode of the Degrees of Freedom project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. The three reactor models we use to determine the fractional conversion and extent of reaction are fractional conversion and extent of reaction models. Treat them as parameters given to you or specified by the problem. These models do not deal directly with either chemical thermodynamics or chemical kinetics. 2. Chemical equilibrium models. Assume the reaction goes to chemical equilibrium and calculate them as the equilibrium values, given the system temperature, pressure, and composition. 3. Homogeneous chemical kinetics models. Use chemical reactor kinetics models, such as batch, CSTR, mixed or stirred tank, or plug flow reactor, PFR, models. These use chemical kinetic expressions, feed conditions, reactor volume, and temperature. These two videos, React but Maintain Your Equilibrium Part 1 and Part 2, introduce the second method, which assumes chemical equilibrium. The first few minutes of this video start from advanced chemical engineering thermodynamics principles to arrive at equilibrium expressions for ideal gases. You are not expected to fully understand the derivation at this point, although we have advanced videos that will explain the concepts in detail. It's just worth being exposed to what advanced level work in chemical engineering is like. Chemical equilibrium thermodynamics teaches that equilibrium is reached when the total Gibbs energy is minimized. Mathematically, this criterion is that the sum of the stoichiometric coefficients of each species, remember again that it's negative for reactants and positive for products, times the reference Gibbs energy for each of these species plus RT times the log of the sum of these activities raised to the stoichiometric coefficients of each species is equal to 0. Or rearranged, we have the product of activities raised to their stoichiometric coefficients is equal to the exponential of minus the sum of the Gibbs energy times the stoichiometric coefficients divided by RT. And we define this quantity to be K, the equilibrium constant. Yes, the A hat sub i's are the activities of the various species. The activity is defined as the fugacity of the species in solution divided by the reference fugacity of that species. What is a fugacity? Again, in advanced courses and later advanced videos, you'll explore what fugacity is in depth. For now, assume it's like a pressure or partial pressure. Anyway, it is measured in pressure units like kilopascals. F hat sub I is the fugacity of species I in solution, like a partial pressure, and F naught sub I is the reference fugacity of species I, like a reference pressure. The sum of the stoichiometric coefficients times the reference Gibbs energy is often written as delta G naught and is similar to delta H naught. K is the equilibrium constant. It varies only with temperature, but pressure has to sneak in here somehow. We'll see how as we continue. What are the units of K? Since the activities are dimensionless, being the ratio of quantities with units of pressure, K has to be dimensionless. For ideal gases, the fugacity in solution is numerically equal to the partial pressure, and the reference fugacity is the ideal gas state at the system temperature and a pressure of 1 bar if you're living in the 21st century. In ancient days, it was a pressure of 1 atmosphere. With these substitutions, the equilibrium constant is equal to the product of the activities raised to their stoichiometric coefficients, which is equal to the product of the partial pressures over the reference fugacity of 1 bar raised to their stoichiometric coefficients. Or, rearranging, the equilibrium constant times the reference fugacity to the overall stoichiometric coefficient for the reaction is equal to the product of the partial pressures raised to their stoichiometric coefficients. K is still dimensionless, but it may not appear to be because of the reference fugacities raised to the overall stoichiometric coefficient. Often you will find that these sort of problems are posed in mole fractions rather than partial pressures, since for an ideal gas, as you'll see in ideal gases exposed, are they even real? The mole fraction is the partial pressure over the system pressure. Or rearranged, the partial pressure is the mole fraction times the system pressure. Substituting into the expression from the previous slide, we get that the equilibrium constant times 1 bar to the stoichiometric coefficient is equal to the system pressure to the overall stoichiometric coefficient, times the product of the mole fractions raised to their stoichiometric coefficients. Or, the equilibrium constant times the pressure to the negative stoichiometric coefficient is equal to the product of the individual mole fractions raised to their stoichiometric coefficients, which it turns out is the equation we're going to use for chemical reaction equilibrium. We might also sneak in pure solids, because the reference fugacity is usually the pure solid, so the activity is exactly 1. You don't actually need to know all of the information before this equation. We just thought you might be curious as to what a more rigorous definition looks like, and where this equation came from. Again, K depends only on temperature, but the equilibrium composition depends on total pressure and the presence of inerts. With a fair amount of calculus, one can show that the derivative of the log of K with respect to T is equal to the heat of the reaction over RT squared, which, if the enthalpy of the reaction is constant with temperature, integrates to the log of K over K naught, is equal to minus the heat of reaction over R times 1 over T minus 1 over T naught. with the temperatures in absolute units. K0 is the equilibrium constant at the starting temperature for the integral of T0. React but maintain your equilibrium part 2 gives an example of applying these principles to a mixture of carbon monoxide, carbon dioxide, and oxygen. The takeaways from this video are 1. The criterion for chemical equilibrium is that the total Gibbs energy of the system is minimized. 2. The equilibrium constant K is equal to the product of the species' activities raised to their stoichiometric coefficients. 3. The equilibrium constant is calculated as the exponential of the negative of the Gibbs energy of reaction over RT. 4. The activity of an ideal gas is the partial pressure over the reference pressure of 1 bar. Thanks for watching. This video was brought to you by the DOFPro team.